Hello everyone, welcome to your next lecture. We are going to continue off where we left off of in our part 1 of linear regression coding section, and we're going to introduce a couple of little extra things and concepts and definitions into your vocabulary. So again, we're still going to deal with the same code. We're going to learn how to build an MLR with machine learning. Split that data, we're going to learn how to use that function, and we're going to deal a lot more with visualization, a lot less with the fundamentals of Python. And then I want to introduce two concepts to you that we're going to go over in greater detail later, the concepts of normalization and overfitting. So later on in this code section, remember that I said we're going to use more than one feature to create our linear regression, our line with machine learning. Things like age are going to be a lot different than things like body mass index or height or weight. So usually standard practice is to change the values of the parameters that we're using into a scale that is consistent between all of them, like between 0 and 1 or -1 and 1. And the reason for that is the learning rate, because the learning rate, if you have like a large learning rate, it might be more large for one parameter than it is for another. And it's losing out on potential learning because there's noise between the different scales of data that it's working with. So in future lectures, we're going to learn more about this normalization process, but I wanted to introduce this to you. The last thing I wanted to talk about is overfitting, and its related concept of underfitting. So the reason that we split data into training and testing is that we don't want our machine learning model to be unable to generalize. Turns out if you train too hard, it's going to just kind of find a very direct relationship between each point rather than being able to be generalized. So we need to be careful that we're not making our machine learning models learn too hard or too specifically. And how we do that is by, there are a couple of tricks to do that, but one of them is to split into training and testing to see if the data can generalize to information it hasn't learned. The inverse of this is underfitting, where you don't give it enough data or enough information or enough learning for it to be able to refine the accuracy and generalize appropriately. It almost is too generalizable, and classes or categories are not being accurately predicted because it's underlearned for some reason, and it might actually underlearn. If you don't normalize, it might underlearn the effect of, let's say, height when compared to BMI. So with those definitions, guys, let's now move into our syntax for this and go back to that code, run a single linear regression, play with some math, as well as look at how that code is running line by line. So I'm going to comment this out. And we're going to look at a couple of these things one at a time. So first, let's print the length of x here and the length of y. Let's just print x so you can see what it looks like. Let us also then print the length of our training data. Okay, and then we will print, let's see what the model looks like. Okay, so when we run this, let's see what we get. So first thing we get is our data frame. There's our x variable. So these are all the values for our body mass index x value. Then we get the length of our x and y variables. So that means there are 440 roughly data points in this data set. And then we printed the length of the training object. And if we did the math, this would be basically 80% of 442. So that training data randomly selected. I'll show you what the training data now looks like, because what we can do is it'll show the row numbers, and you'll see that it selected a bunch of random rows one at a time. See? So the first thing you see here with the pandas data frame is these values are the index position, and then this is the actual value. So this is saying it selected row 106, 343. So not only is it not in order, but it selected them at random. Okay? So it's a random selection of 80% of the data. And then the last thing that printed is this linear regression parameter stuff. So it fit to an intercept, it only did one job, it didn't try to normalize data, and it just copied the X value, okay? So that was all the default parameters that we could adjust in this model that we're not right now. So one thing I want to do now is I also want to just show you a classic linear regression analysis, as well as compare that linear regression to our mean squared error and like our basic calculations here. So what this is doing, this is going to create our function for our linear regression, our standard linear regression. If you took my previous class on Introduction to Python, this is our statistics class, and basically what we're doing is we're using NumPy here, and we're saying, okay, you know, give our X variable, our Y variable, and calculate a linear regression, and then create the function for that linear regression once you have the parameters. So, you know, an mx plus b. So I'll print the mx plus b here, and we'll look at what that graph looks like, okay? So first things first, let's also take that off. There we go. So first we get the function right here. And so we see that it's like, you know, almost like basically around 1,000 x, and that makes sense because we are, you know, at 100ths here, and it might go up in that value. Oh, let's also take out the blue here for a second. And what else do we have? We have the intercept at 1512. So if we're at 0 here and we go all the way up, it looks about 152 here to me as well. So that function is actually correct. The intercept is at 0 there. So what I then want to show you is the set of predictions that the machine learning regression model did and how they relate to that line. So we got that there. Run. There we go. And that was what we recreated before. Remember, this is from our first class. So it's following that linear regression line. This code here, what this is our matplotlib code. So remember what we're doing here is that we first create a figure container and a set of access parameters by using plot.subplots. The subplot default is just one graph, so I didn't set columns and rows and total number of plots. I then passed in the X and Y data for this single feature and said I wanted red dots. I then provided the X again and fed X into our linear regression function to get Y, and I said I wanted black dotted lines. And then I also plotted our machine learning model here. This thing here, what's going on here is I'm passing in some X data that our machine learning model never saw. And I'm saying, okay, give me a Y for this data. And with predict and the list of values, it will return a list of predictions. So this predictions is a Y value here. So I'm saying, okay, here are our X's and here's the predictions from our machine learning model as opposed to our linear regression function creation. And I want those as blue dots. And then I adjusted X labels and Y labels. I added grids so it would be easier to see where the y-intercept was. And then I said, okay, let's just show this graph on Jupyter Notebooks. That's all that code is doing. If you want to learn more about visualization, I recommend you also go back to my previous class. So what we get is that there. The next thing I want to show you is, okay, we have this R value, P value. We don't really need to see that right now, I think. Yeah, what we're instead going to see is, so we have our predictions like we did before. And what I did instead is rather than get the train data, I took all of the X data and I created the prediction, our prediction list. Now remember, that's that YI with the tilde on top, our set of predictions. So if I end up calculating our mean squared error, like I showed you last time, the sigma n over I equals 1, sum of the actual targets to the predicted targets, and I square that, I should get the mean squared error, okay? So when I run that, what you'll see is, okay, first thing is I have to actually show you this part of it. I don't have to show you the R or the P value, but this thing called standard error here is basically the mean squared error divided by the population. And this is just a way of standardizing how large the mean squared error is so that it's like within a certain range that's more standardized across all data sets. So what we do is I make our predictions here. I then calculate our mean squared error, our y to our set of predictions, squaring it, like basically checking the distances between our predicted values, our blue, and our y values for that thing. And I computed, that's the mean squared error, which I'm just saying squared here. And then lastly, the standard error is eliminating the squaring by taking the square root and then dividing the mean squared error by the total population, okay? Or the total length of data. And so if we compare our standard error from our linear regression to our hard-coded standard error from our machine learning, what do we get? We set these two values here. And what this is saying is that the mean squared error is not exactly the same in terms of calculation as it is in the machine learning model. It's actually arguably slightly better, it's saying here, slightly more accurate without doing any kind of like parameter tuning. But it's also saying that it's calculating mean squared error, and there are like basically very, very small differences in rounding that are making up for some of the differences in these values here too. So pretty cool. The mean squared error is actually being found in a completely different method than using our standard method. Last but not least, I want to just show you how this works with multiple features now. So the difference between last block and this one is that now features isn't just BMI. It is all X categories that are available in our data frame. You can't do this that easily with a standard linear regression. Everything else is basically the same. And so we're going to have a completely different x-axis. It's not BMI anymore. It's an integration of data from various targets or various categories along with the score. And what happens when we do this? So first off, visually, it appears to have created a small linear regression line somewhere like there, but it doesn't appear like it would be very accurate because look at the spread of data. So an interesting thing about machine learning is the more data that you have, the more different types of information, the more difficult it is to find these natural patterns. So even though we were able to create a linear regression with all these features, we need to do a handful of other things such as parameter tuning, optimization with respect to normalization. So, we have an age variable and a height variable, which are going to be different in terms of their scale. Like, okay, so height is in centimeters, let's say, 124, and you have ages in years. Usually with machine learning, we want to normalize our variables to be close to each other in terms of their ranges, because then when we do our step sizes, each of those parameters are actually being adjusted in similar ways. There's also better ways of doing training and testing, for instance. So this is an example of showing you how all this machine learning machinery works under the hood, but also how important parameter tuning is and understanding the nuance between just like plugging in an X and Y and seeing what it can predict. So in other classes, not only are we going to learn more about doing like different types of machine learning models, I'm going to continue to introduce best machine learning practices, such as normalization of your parameters, such as learning about overfitting and underfitting, and local and global minima. All of that stuff is very important. So let's recap, guys. What did we learn today? What we learned is that we learned how to build a multiple linear regression model using machine learning very simply. We played with single variables as well as multiple variables in order for that machine learning model to be created. But we learned that there's more nuance there and that more has to be done in order to prune and process our data that we're going to get introduced to slowly through this class. We got a little bit of a reminder of how Python works by like importing objects and lists and all that kind of stuff. I showed you a simple way of building training and test objects for your data using scikit-learn, and we did a little bit of visualization.